So the time has arrived for us to finish the proof of the fact that this deterministic selection algorithm based on the median of median ideas does indeed run in linear time. We've done really all of the conceptually difficult work. We discussed the algorithmic ingenuity required to choose a pivot deterministically that's guaranteed to be pretty good. So remember, the idea was you take the input array, you logically break it into groups of 5, you sort each group. That's like the first round of a 2-round knockout tournament. The winners of the first round are the middle elements of each group of 5s. That's the initial set of medians. And then the second round, we take a median of these n/5 first round winners, and that's what we return as the pivot. And we proved this key lemma, which is the 30/70 lemma, which says that if you choose the pivot by this 2-round knockout tournament, you're guaranteed to get a 30/70 split or better. So your recursive call in line 6 or 7 of deselect is guaranteed to be on an array that has at most 70% of the elements that you started with. In other words, you're guaranteed to prune at least 30% of the array before you recurse again. But what remains to understand is whether or not we've done a sensible trade-off. Have we kept the work required to compute this 30/70 split small enough that we get the desired linear running time? Or is the cost of finding a pretty good pivot outweighing the benefit of having guaranteed good splits? That's what we got to prove. That's the next subject. Here's the story so far. You'll recall that, as usual, we define T of n to be the worst case running time of an algorithm, in this case deselect on input arrays of length n. And we discussed, okay, there's the base case as usual, but in the general case, we discussed how outside of the 2 recursive calls, the deselect algorithm does a linear number of operations. What does it have to do? It has to do the sorting, but each sorting is on a group of size constant of size 5, so it takes constant time per group. There's a linear number of groups, so step 1 takes linear time, the copying takes linear time, and the partitioning takes linear time. So there's some constant c, which is going to be bigger than 1, but it's going to be constant, so that outside of the recursive calls, deselect always does at most c times n operations. Now, what's up with the recursive calls? Well, remember, there's 2 of them. First, there's one on line 3. This is responsible for helping choose the pivot. This one we understand. It's always on 20% of the input array, namely the first round winners. So we can very safely write T of n/5 for the work done, in the worst case, by that first recursive call. What we didn't understand until we proved the key lemma was what's up with the second recursive call, which happens on either line 6 or line 7. The size of the input array on which we recurse depends on the quality of the pivot, and it was only when we proved the key lemma that we had a guarantee on the quality of our pivot. 30/70 split or better, what does that mean? That means the largest subarray we could possibly recurse on has 7/10 n elements. So what remains is to find the solution for this recurrence and hopefully prove that it is indeed big O of n. So let me go ahead and rewrite the recurrence at the top of this slide. We're not really going to worry about the base case T of 1 equals 1. What we're interested in is the fact that the running time on an input of length n is at most c times n, where again c is some constant, which is going to have to be at least 1, given all the work that we do outside of the recursive calls, plus the recursive call on line 3 on an array of size n/5, plus the second recursive call, which is on some array that has size, in the worst case, 7/10 n. So that's cool. This is exactly how we handled the other deterministic divide and conquer algorithms that we studied in earlier videos. We just wrote down a recurrence, and then we solved the recurrence. But now, here's the trick. In all of the other recurrences that came up, for example, merge sort, Strasson's matrix multiplication algorithm, Karatsuba multiplication, you name it, we just plugged the parameters into the master's method, and because of the power of the master method, boom, out popped up an answer. It just told us what the recurrence evaluated to. Now, the master method, as powerful as it is, it did have an assumption, you might recall. The assumption was that every subproblem solved had the same size. And that assumption is violated by this linear time selection algorithm. There are 2 recursive calls. One of them's on 20% of the original array. The other one is probably on much more than 20% of the original array. It could be as much as 70% of the original array. So because we have 2 recursive calls and subproblems of different size, this does not fit into the situations that the master method covers. It's a very rare algorithm in that regard. Now, there are more general versions of the master method, of the master theorem, which can accommodate a wider class of recurrences, including this one here. Alternatively, we could push the recursion tree proof so that we could get a solution for this recurrence. Some of you might want to try that at home. But I want to highlight a different way you can solve recurrences just for variety, just to give you yet another tool. Now, the good news about this approach that I'm going to show you is that it's very flexible. It can be used to solve sort of arbitrarily crazy recurrences. It's certainly going to be powerful enough to evaluate this one. The bad news is that it's very ad hoc. It's not necessarily very easy to use. It's kind of a dark art figuring out how to apply it. So it's often just guess and check is what it's called. You guess what the answer to a recurrence is, and then you verify it by induction. Here, because we have such a specific target in mind, the whole point of this exercise is to prove a linear time bound, I'm going to call it just hope and check. So we're going to hope that it's linear time, and then we're going to try to produce a proof of that, just that verifies the linear time bound using induction. Specifically, what are we hoping for? We're crossing our fingers that there's a constant. I'm going to call it A. A could be big, but it's got to be constant. And again, remember, constant means it does not depend on n in any way, such that our recurrence at the top of this slide, t of n, is bounded above by a times n for all n at least 1. Why is this what we're hoping? Well, suppose this were true. By definition, t of n is an upper bound on the running time of our algorithm. So if it's bounded above by a times n, then it's obviously O of n. It's obviously a linear time algorithm, where a is the constant that gets suppressed in the big O notation. So that's the hope. Now let's check it. And again, check means just verify by induction on n. So the precise claim that I'm going to prove is the following. I'm going to go ahead and choose the constant a. Remember, all we need is some constant a, no matter how big, as long as it's independent of n. That'll give us the big O of n time. So I'm actually going to tell you what a I'm going to use for convenience. I'm going to choose a to be 10c. Now what is c? C is just the constant that we inherit from the recurrence that we're given. Now remember what this recurrence means. This is what the running time is of the deselect algorithm, and the c times n represents the work done outside of the recursive calls. So this is just the constant multiple on the amount of linear work that deselect does for sorting the groups, for doing the partitioning, and for doing the copying. Okay, so there's going to be some small constant, reasonable constant, and for the proof I'm just going to multiply that by 10 and use that as my a. And the claim is, if I define a in that way, then indeed it is true that for all n at least 1, t of n is bounded above by a times n. Now I realized I pulled this constant a out of nowhere, right? Why 10 times c? Well, if you recall our discussion when we proved that things were big O of something else, there again there was some constant. So to formally prove that something is big O of something else, you have to say what the constant is. And in the proof, you always wonder, how do you know what constant to use? So in practice, when you're if you have to actually do one of these proofs yourself, you reverse engineer what kind of constant would work. So you just go through the argument with a generic constant, and then you're like, oh, well, if I set the constant to be this, I can complete the proof. So we'll see that's exactly what's going to happen in the proof of this claim. It'll be obvious. The very last line, you'll see why it shows a equal 10c. So I just reverse engineered it for what I needed for the proof. But to keep the proof easy to follow line by line, I decided to just, full disclosure, tell you the constant right at the beginning. Now, no prizes for guessing that the way this proof proceeds is by induction on n. Induction is the obvious thing to use. We're trying to prove an assertion for every single positive number n, and moreover, we're given this recurrence, which relates solutions of smaller subproblems to that of bigger problems. So that sets things up for use of the inductive hypothesis. If you want a longer review of what proofs by induction are, I suggest that you go back and rewatch the optional video where we prove the correctness of quicksort. There's a fairly formal discussion of what the template is like for a proof by induction, and that's the one we're going to apply here. So there's two ingredients to any proof by induction. There's a usually trivial one in the form of a base case that's also going to be trivial here. So in the base case, you just directly establish the assertion when n equals 1. So we're trying to prove that t of n is at most a times n for every n. When n equals 1, if we just substitute, then what we're trying to prove is that t of 1 is at most a times 1, also known as a. And we're given that t of 1 is 1. Right? That's the base case of the recurrence that we're given. So that's what we're using here. What we want to be true is that this is at most a times 1, but it is. So the constant c, we're assuming, is at least 1. So certainly if you multiply c times 10 to get a, it's definitely at least 1. So the right-hand side here is unquestionably bigger than the left-hand side. A, in fact, is even bigger than 10, let alone bigger than 1. So the interesting ingredient is generally the inductive step. So remember, what you do here is you assume you've already proven the assertion, that in this case the t of n is at most an, for all smaller integers, and now you just merely have to prove it again for the current integer. So we're now interested in the case where n is bigger than 1, and the assumption that we've already proven it for everything smaller is called the inductive hypothesis. So what does it mean that we already proved it for all smaller numbers? It means we can use in the proof of our inductive step the fact that T of k is at most A times k for all k strictly less than n. All we got to do is enlarge the range of n's to which this holds to one more, to the current value n. And all we have to do is follow our nose. So pretty much we have to start on the left-hand side with T of n. We have to wind up on the right-hand side with A times n. And pretty much at every step of the proof, there's just going to be one conceivable thing we could do. So we just follow our nose. We start with what we want to upper bound, T of n. Well, what do we got going for us? The only thing we can do at this point is invoke the recurrence that we were given up here. So we have an upper bound on T of n in terms of the t value of smaller integers. So we are given that T of n is at most C times n plus T of n over 5 plus T of 7/10 n. I'm of course ignoring fractions. You would round up or round down if you wanted to be precise, and the auxiliary lecture notes are more precise if you want to see what the gory details look like. But it's really just exactly the same argument. One just has to be a little bit more anal about it. So now that we've invoked the recurrence, what can we possibly do? Right? We can't really do any direct manipulation on any of these three terms, but fortunately, we have this inductive hypothesis. That applies to any value, any integer, which is less than n. So we have here n over 5, that's certainly less than n. We have 70% of n, that's certainly less than n. So we can apply the inductive hypothesis twice. We already know that these t values are bounded above by a times their arguments. So T of n over 5 is at most a times n over 5. T of 7/10 n is at most a times 7/10 n. Now we can group terms together. Now we're comparing apples to apples. So we have n times quantity c plus a over 5 plus 7/10 a. Let me just go ahead and group the two a terms together, and that's going to be 9/10 a. Now don't forget where we're going, what the end goal is. We want to upper bound T of n by an, so we want to write that this is bounded above by a times n. And now you see exactly how I reverse engineered our choice of a as a function of the given constant c. Since a is 10 times as big as c, if I take 90% of a and add c, I just get a back. So by our choice of a, this equals an. And that pretty much wraps things up. So don't forget what all this stuff stands for. So what did we just prove? What did we just prove by induction? We proved T of n is at most a constant times n for every n. That is, T of n is big O of n. What was T of n? That was the running time of our algorithm. That's what we cared about. So because T of n is big O of n, indeed deselect runs in O of n time.